informal. Okay, let me see if I can expand that to the whole screen. Okay, so that should be good. And yeah, so I think all this work with teaching online, like it's inspired me to start using experimenting with different ways of presenting. As here we're trying out the handwriting typeface, and we'll see how that goes. But the topic is uniformization of metric surfaces. And just to give a bit of motivation here, just the simplest example you can probably think of would be a one-dimensional curve in the plane. And here there are two main ways you can think about that object. You can think about it intrinsically in terms of some kind of geometric condition that a set of points in the plane satisfies, or maybe like a solution set of an equation. Or you can think of the curve parametrically as being identified with a map from an interval or a circle. And just an example of this is that any curve of finite house of one measure, or finite length, you can always find an arithmetic parametrization of that curve. And it gives two different ways of thinking about the same object. So now this line of thinking, if we're thinking historically, so back in the 1800s, this was applied to the case of surfaces. And so you might imagine, say, a pair of complex variables satisfying some type of algebraic relation. And what they try to do is express one of these variables as a function of the other. It's in that sense, I guess the same idea of trying to think of the surface in terms of that particular parametrization. I mean, that was the origin of the uniformization problem historically. And the culmination of that in the 1800s was the classical uniformization theorem of Poincaré and Courbe. And in today's terms, we say that every simply connected Riemannian two-manifold can be mapped conformally onto either the disk, the plane, or the sphere. And conformally here just means that a small ball, or an infinitesimal ball, gets mapped onto an infinitesimal ball in the target space. So that motivates the following basic question that we're going to focus on for the rest of the talk. And that is, if you have a metric space homomorphic to R2, what are the possibilities for this? What does such a space look like? And at this point, it's still a bit too broad to answer. And so typically one can make progress by imposing some type of geometric condition on the space. And perhaps the two most basic that come to mind would be, you might assume that you have a length metric space. So that just means that the distance is obtained by infinitizing over lengths of paths. And then another possibility is just to assume that you have a space of locally finite house of two measure. And that would rule out, say, like a fractal space. And that would be important if you want to use analytic techniques to study them. So now before we go any further, we can ask, well, what's the motivation? And very briefly, I want to point out three different connections. And instead of explaining them, I'll just give a representative reference for each of these. So the first is to geometric group theory. And this relates to problems such as Cannon's conjecture about the boundary of word hyperbolic groups. And so I've listed a reference just for that problem. Another direction is in complex dynamics. And for this, I suggest the book Expanding Thurston Maps by Mario Bonk and Daniel Meyer. And then the final direction would be minimal surfaces. Because by definition, a minimal surface is an area minimizer. But typically to find them, you look for parametrization, which is energy minimizing for some type of energy. And that corresponds to a conformal map, or at least an almost conformal type of map. And for that, I'd recommend work of Alexander Lubchak and Stefan Wenger. Okay, so getting back to the topic of geometric assumptions that you might use to build a theory. One possibility, if we go back a few decades, is that if curvature either bounded above or below. And this point of view led to the theory of surfaces of bounded curvature, or more precisely, locally bounded integral curvature. And this was a topic of study mainly by Russian mathematicians beginning in the 1940s. So people like Alexander Alexandrov and people around him. And one thing to keep in mind is that this is still a relatively rigid requirement. So a space of bounded curvature, they have conformal parametrizations, and at most points they're going to be bi-Lipschitz equivalent to a Euclidean disk. So now moving beyond that, you might look at other types of assumptions, and you have a great number to choose from that have been examined and studied in great detail. And here are a few of the main ones. So first, you might assume that the space has a quadratic mass bound. So either from above or from below or both. And in the literature, this is typically called offers 2 regular. So take that as an assumption on the space. Another one is a geometric condition called linear local connectivity. And just intuitively, this would rule out cusps and similar geometric features from a space. Next, you can look at an analytic condition, like the Poincare inequality. And for this would just say intuitively that the mean oscillation of a sufficiently differentiable function is controlled by the gradient of a function in a specific way. The next one would be bounds on the conformal modulus of curve families. And the conformal modulus is, so this is an invariant, a conformal invariant studied in beginning and complex analysis, where to each curve family, you associate a number measuring the size of that curve family in a conformal invariant way. And so if you assume bounds on that, then that's also been a fruitful place of departure. And the final condition here would be the validity of a quadratic isoparametric inequality. And this just means that if you have a curve, so any curve of finite length, it bounds a disk, and the area of that disk is no more than the length squared of the curve up to some multiplicative constant. So all this has been studied in great detail. So all those are conditions on the space, and then you might ask about maps. And there are 3 main categories of maps that come up in this context, which I've listed here. The first is bi-Lipschitz maps. And these roughly preserve the absolute distance between pairs of points. Next, we have quasi-symmetric maps. And this roughly preserves shape. If you have triple of points, the relative distance between those between that triple is roughly preserved. And then finally, we have quasi-conformal maps. And these can be defined in a couple of different ways. But here we'll just say those that quasi-preserve the conformal modulus of curve families. So an example of this type of approach, we have a kind of a prototypical theorem of Mario Bonke-Bruce-Kleiner, and it states that if X is any metric space homomorphic to the sphere, which is alpha 2 regular, then you can find a mapping onto the 2 sphere, which is quasi-symmetric, if and only if the space is linearly locally contractible. And just the main thing I want to emphasize here is just the form of the theorem, that the existence of a certain type of parametrization is equivalent to a geometric condition on the space. In other words, from that geometric condition, you can construct, as it were by hand, a mapping with strong geometric properties. So in connection with this, I'll mention just a result of my own. And this was a question that existed for some time in the literature, and that is if you have a quasi-symmetric map from the 2 sphere onto just some surface, can it take a set of positive 2 measure onto a set of measure 0? This is called the inverse absolute continuity problem. And it turns out the answer is yes, you can give examples as basis with that property. And actually with Demetrios in the department, we actually proved that to show that the space could be taken to be a surface in R3. So next, I want to talk a little bit about the quadratic isoparametric inequality. And this has been studied extensively by Alexander Lipchak and Stefan Wenger. This is a basic axiom in these geometric types of problems. And one result that is, you might say, is the culmination of the whole approach is the following theorem. And it says that non-positive curvature can be characterized precisely in terms of the quadratic isoparametric inequality with the Euclidean constant. So if you have a proper length space, it's at zero if and only if it has the Euclidean isoparametric constant. And in my most recent project, this is with Paul Preuss at the University of Cologne. We investigated the borderline case. So in other words, you could take this Euclidean constant 1/4 pi and just replace it with something slightly larger. What kind of possibilities or restrictions happen there? And just to summarize very roughly is that we showed these nice geometric properties that a cat zero surface would have. So these are lost as soon as the Euclidean constant is replaced with anything larger. So you can construct examples where you have kind of this degenerate geometry is measured by, for example, the quadratic mass band that would fail on the structure minimal surfaces. That's not as well behaved as soon as you replace this Euclidean constant with anything larger than that. So that's what I prepared. So feel free to ask any questions that you might have.